Okay, so welcome to our third and final workshop in our series. Today, we're going to be talking about some tips and tricks that we've learned for building and designing robots. And hopefully you'll be able to get something out of this that will not only help you in creating a robot that you're proud of and a design process that's reliable, but also hopefully a design process that will help you with awards and similar things along those lines. So we're going to start with our design process. Just talk about some of the things that we keep in mind when going through this from the start of our mechanisms all the way through to the end of our mechanisms. So we typically think of our design process in 3 chunks. You can see the full list here over to the side. We're going to dive into those and go into a little more depth. But the basic idea is we start off with the first part where we generate all of our ideas for our different mechanisms. And this is entailed by the read and understand the game manual, brainstorm, research, and prototype phases. These are sort of where we get all of our ideas. Then we have our testing, selecting a design, and designing the mechanism. This is where we sort of come up with what the mechanism is going to look like in a more fully fleshed out way. And then finally, we have our testing, iterating, and refining phases where we take our design that we have created based off of the prototyping and brainstorming, and then we make it better and polish it and have it that's something that's more competition ready and that can score us more points. So starting off with that first section,
Right, yeah. So the first step, these are the first steps to designing a robot. So we start by reading the game manual as a team so that everyone is on the same page for what game tasks that we want to prioritize based on point value and amount of effort. So then after that, we brainstorm in two phases, divergent. So that's where we come up with as many ideas as possible, no matter how crazy, and convergent, where we combine ideas and pare it down to more viable solutions. Ideally, there should be several ideas per mechanism going into prototyping, and we draw inspiration for brainstorming from FRC teams, other FTC teams, and industrial examples. You can look on YouTube, FTC forums, FTC subreddits, etc., to see what others have done in the past for inspiration.
So you want to come out of brainstorming with several different prototypes per mechanism. This way you can rapidly create prototypes and proof of concepts that have separate concepts, but function as the same purpose for your robot. This way you have as many ideas as possible, a wider variety of things that you can test and figure out what works for you and what doesn't. If you can find a way to empirically test these mechanisms, so like, for example, for an intake, you test how many times it intakes successfully or the speed that it intakes successfully, and you can run multiple trials. We try to do 5 trials per test. If you can find a way to do that empirically, then that will give you good data for your notebook, as well as it will give you a very objective way to figure out what is worth pursuing. So if you have an intake that's overhead using noodles that you measure how long it takes to intake whatever you're intaking, and that works faster than, say, some side spinning compliant wheels, and you test that and you run it 5 times and the average speed is faster with the first one, then you know that's what you want to pursue. And you can do that because you took the parallel prototyping process and had several different prototyping concepts per mechanism that you were able to empirically test. Once you have done those tests and you know what you're going to pursue, then you are going to want to make a more finalized design. And we use CAD for this. The software that we use is SolidWorks. SolidWorks is a very expensive software, but they do offer sponsorships for their desktop licenses for FTC teams. Some other free options are some things you may be familiar with, such as Onshape or Autodesk Inventor. And one of the key parts of taking something from a prototype into a more fleshed out design is that you want to rely on the learnings that you gained from your prototype. You don't want to be majorly tweaking your concepts or anything, because then you could be introducing new untested variables or concepts that could backfire in certain ways. So what you want to do is take your concept from prototyping, mock it up in CAD, design it using the parts that you have that are going to stay together, and then test it again to make sure that it is working and that your concept hasn't changed in any drastic ways from your prototyping testing to your actual design. So then once you have done this for that mechanism and you have done the testing, you have to figure out what you could do to make it faster. So let's go back to our example that we were using earlier with our intake. We have tested this overhead spinning noodle intake, and we know how fast it takes in our minerals. But let's say there's some place in going from on the field to inside the robot where it's sticking somewhere, or maybe it's rattling out and it's not intaking them all the time. You want to do those multiple tests again. We try and do 5 trials per test, and you want to isolate the things that are causing you to lose either time or points or consistency or whatever that is. Anything that is causing your mechanism to not work well and not work every time, or anything that is causing your mechanism to not work as quickly. That is something that you want to test, change in your design, and then address and fix, and then keep on doing that testing and just keep on feeding back and iterating. The more times you iterate, the closer you will get to a more efficient and more accurate design as well. The more you test and document and iterate, better that will look for awards. So again, say there's a cube that you've tested, and your whatever you're intaking, whatever field game element that you're trying to intake is getting stuck. You figure out where it's getting stuck and you sand it down or take that out of your design. Or if it's like bouncing out, maybe you add some guards to keep it into where it is, and then you test again, and hopefully that improves your performance or consistency or whatever it is that you're going for.
In FTC, the drivetrain is one of the most critical structures for an FTC robot. So there are many different types of drivetrains, but we will be going over the 7 main types that all have advantages and disadvantages over in this slide. So for considerations you should be considering is speed, or how fast the robot can move across the field, the power of the drivetrain, which it doesn't have enough torque to move your robot around the field, maneuverability, how easy and fast can you move and rotate to get to a certain position on the field. The traction is how easily can your robot be pushed around or get over and move across the field tiles. Terrain is how can your robot move over or around obstacles to get to where you want to be. And omnidirectional is somewhat to help maneuverability by moving your robot in different directions without turning it. The 4-wheel drivetrain is one of the most common drivetrains, which also has a few different variants. The 4 traction wheels is harder to push around and harder to maneuver, but this robot is fast because the motors are directly connected to the wheel, because they'll allow for less air within the gears or sprockets slipping. On the 2 traction 2 omni wheel drivetrain also is a good pick for but the center of rotation is closer to the traction wheels because the omni wheels are easier to move around. Is still hard to be pushed around on the field. It has still some good maneuverability too. And finally, the 4 omni wheel drivetrain has good maneuverability with good turning, but it's really easy to be pushed around the field. And there's also the 6-wheel drivetrain, which is definitely a higher traction than the 4-wheel drivetrain. It's better to cross over difficult terrain because you have the middle wheels added to it, which would allow your robot to glide over there much easier. The direct motors also make this robot faster than other robots. This robot tends to not strafe as much in most designs. And this robot takes up a lot more space with those extra wheels and bulkier sides.
All right, so this is a mechanism drive. It's one of the most commonly used drives in FTC. Some pros of it is that it can strafe because it has the little rollers on the wheels. It has extremely high maneuverability due to the ability of that, or the fact that it can strafe. And it's useful in most cases. It's very versatile. Some cons of it is that it only works on a flat field without custom design work. Like this past year in the game, there was bumps on the field that you could either drive over or maneuver around, and the robot that our team built had raised like a raised drivetrain because of we had to do custom design work because it was on that was not a flat field, and it's slightly complex to program because it all the wheels are at 45-degree angles, so that can make it difficult to program.
X-Drive is similar to the Mecanum drive in that it can strafe in any direction, but it's similar to your four-wheel drivetrain because it has fairly low traction because it can slide in any direction. So if you have an X-Drive, it's pretty easy to be pushed around, but it is very maneuverable because the wheels can rotate against each other in order to produce movement in any direction that you want to. One of the issues with X-Drive is that as you can see in the depiction there, all of the motors are facing in towards the center. So without some beveling, like bevel gear driving or some round belt driving, the motors are going to be at a strange angle because all of your wheels are at 45 degrees. Something to note, though, is that there's an alternative wheel configuration that's sometimes referred to as a box drive, where instead of having all four of your wheels in the corners, you have one wheel on each side running parallel to that side, and it offers the same maneuverability and the same traction. It's basically the same drivetrain, but it's a little bit easier to place the motors for, and it looks a little bit more conventional.
The Ace drivetrain is a better maneuverable robot than the four-wheel drivetrain. It can strafe to the side with that fifth wheel in the middle of it, and it can use, but it uses an extra motor that is needed for the middle side, which is a disadvantage to the rest of your robot because you are missing that robot from the motor from the rest of your robot. It can still easily be pushed around like the four-wheel drivetrain can, and it uses up a little more space than needed to achieve the same thing that either the X drivetrain or the Mecanum drivetrain can do. And finally, the tread drivetrain is has good traction with the tank treads over easy terrain, but it has very bad maneuverability with the tank treads, and you have to get really good quality of tank treads to make sure they don't snap in the middle of a match or something.
So our final drivetrain is the Swerve Drive, and this is pretty much ticks all of the boxes, whereas it's maneuverable. There's a great amount of traction, and you see this a lot of times in RC, which is has heavier robots that can push each other around a lot more, so they need something that has traction and is very maneuverable. The issue is, though, that it's very space consuming and very complicated to design. So the risk versus reward in FTC, you don't see it that often. Usually people will go for Mecanum because it offers enough traction that you're not going to get pushed around willy-nilly, but it's a lot simpler to do than Swerve. And additionally, Swerve drivetrains will eat up 4 of your motor slots like most drivetrains will, but additionally, it will take up 4 servo slots. So you're have a little bit less flexibility of where you can use servos elsewhere because you're using 4 of your servos that you have allotted on your drivetrain. And then something that we forgot to mention at the beginning of this presentation, but we did mention in chat, is that throughout this presentation, if there's anything that we're talking about that you don't understand or would like to know more about, you can just simply put that in our chat, and we will read out that question during these question breaks which we have throughout the presentation. So I see one here that asks, can't you just add a suspension system with a small amount of travel for Mecanum or for really most drivetrains? And this is true. You can add suspension systems. There are several different ways of doing this. We looked at doing this last year for having where we had a center bar that would go across two different pods of Mecanum drive, and we have springs that would try and keep it back to an equilibrium. And as it would go over a barrier, it would deform and make the travel more smooth. So that is something that you can do for most drivetrains. We're just going over some of the simple motor configurations. The next question is, can't you connect the other motors to the middle wheel in the H drive? Then you would not have an extra motor. The issue with this is that the H drive is basically your four-wheel omnidirectional drive, which can move forward and backwards, and then you're adding that extra omnidirectional wheel into the center so that you can move side to side. So in theory, what you could do is you could drive your left side with one motor by itself and your right side with one motor by itself, and then give your center wheel its own motor, and then that would take it down to 3. However, driving entire sides of a drivetrain with one motor is not something that I would entirely recommend, because it gives up a lot of your torque and a lot of your power, and you would still it'd be very easy to push you around the field because you're entirely on all of those omnidirectional wheels, so you can still slip and slide anywhere. Let's see. Most of these drivetrains have 4 wheels with motors. Are there benefits of using Are there benefits using 2 motors, either front and rear with chain link, or gear driving other set? So that kind of goes back to what I was talking about with the H drive. There it is. You will get the similar amounts of maneuverability. Like I said, with using one motor per side of your drivetrain. So like driving both of your left wheels off of a motor and both of your right wheels off of a motor. The issues are, though, when you get to things that aren't H drive or that aren't your 4-wheel drivetrain, things like X drive and Mecanum drive, you do need a motor for each one of those individual wheels, because you have them turning in opposite direct. You have wheels that will be on the same side turning in opposite directions some of the time, or in the same direction depending on where you're trying to strafe to. So some of the advantages of 4 wheels is that in some of the more complicated drivetrains, like your X drive, or your box drive, or your Mecanum drive, you do need individual motors for every one of your wheels so that you can strafe in all the directions that you need to. And additionally, it also adds more torque and more speed to your, basically just more power to your drivetrain. But there are some cases where you can't get away with using a motor per side. And then again, if you're doing that with an H drive, you would need a 3rd motor for your strafing wheel. Our team uses Mecanum drive. We use GoBuild Kit parts, which we'll talk about briefly later on, but GoBuild offers a strafer kit. We do not use their strafer kit, but we typically use their low side C channel and their high side C channel in order to create a Mecanum drivetrain, and we use custom pulleys to get a gear ratio that works for us. We'll talk more about gear ratios and belt drives in a little bit, but I highly recommend the GoBuild a Mecanum wheel kit. Their Mecanum wheels, even if you don't get their strafer chassis that they have, their Mecanum wheels are just very high quality, and that's what we have experienced to be the best. And in the past, we've used, instead of using their kit parts, we've done custom cutting things, and as Malia mentioned earlier, in order to get the correct geometry. But that's what we've experienced. We're good to move on. All right, drive methods. So as I mentioned earlier, while I was answering those questions, drive methods such as direct drive, chain drive, belt drive, and gear drive, these are great ways to get power from your motor to whatever you're driving, not necessarily a wheel, but whatever you need to turn. These are great ways to do that, and they're very helpful for drivetrains or really any mechanism. So the first thing that you need to understand for different driving methods is gear ratios. Gear ratios will change the so for any given motor, there is a set amount of maximum amount of torque or maximum amount of speed that you can get out of that motor. And if you gear it more for speed, you'll have less torque. And if you gear it more for torque, you'll have less speed. And that's just how it is. So the way that you get those different gearings, though, whether you want more speed out of it or more torque out of it, is by changing the diameters of your driven and driving components. So you'll see in this this illustration here, your driving component, that would be what you would attach to your motor, in this case, is twice as large as what we're driving. So this would be, in the case of a drivetrain, that would be something like a belt going to a wheel. And if you have this belt going around these, what would be pulleys for a belt, if your pulley that you put on your motor is twice as big as the pulley that you would attach to your wheel, then that would be a 2-to-1 gear ratio, and your wheel will spin twice as fast as it would if you were just attaching it directly to the motor. Some things that you should think about when you are thinking about gear ratio that may not be inherently evident is that gear ratios come from places that you may not think. Like, for example, in a drivetrain, the size of your wheels plays into the gear ratio that you get from your drive motors. So if you have very large wheels, then you will get a more of a gear ratio towards speed. And if you have very small wheels, then your robot won't move as fast because it'll take more rotations to get this to the same distance.
One of the first methods you can do is a train drive. This is the easiest way to make the length of the chain longest or shorter, because with other methods you would have to do it. You'd have to get a completely different belt or something like that. And it's quick to fix how long or short you want your chain width by just adding or removing links to it. And it is often requires some sort of proper tension. So either you're going to have to get your chain distance perfectly away from each other so it can easily get on, or you're going to need some chain tension, some method to keep your chain from possibly coming off. And over time, this chain does break as well as stretch, especially when you have your tension so tight. The chain will tend to stretch within a few months, and you'll have to replace it eventually. And it can, and then yeah.
And another driving method, which is not so much a driving method because this is the simplest way to do it, and the only gear ratio that you're getting would be the gear ratio that is in the motor gearbox, is direct drive. This is when you simply slap a wheel onto the shaft of your motor, and you're just dealing with whatever out of the box your motor power is. And this is definitely the easiest way to do it. And like if you're making a simple 4-wheel drivetrain, you just throw your 4 motors on with the shafts sticking out, and then you put your wheels on, and then you power your motors, and you've got a really simple drivetrain or whatever mechanism that you're creating. There are some issues with this though. And the issues that you will find is that when you put something directly on the shaft of your motor, you are causing stress to your motor that you would not get if you had otherwise driven it through chain or belt, and because all of these things also take off stress. Also, you're going to always have your motor sticking out of wherever your driven component is. You're going to have this giant space-consuming object that is at a place where you cannot put anything else, and its only purpose is to drive whatever you're driving, which may be fine if this is something that you put into your design considerations. But a lot of the time, where you want your motor to be is not right where you want your driven component to be. And so that's why things like belts and pulleys allow you to, that flexibility comes in handy. And then belt drive, similar to chain drive, in the fact that you have a lot of flexibility in your gear ratios and a lot of flexibility in your motor placement, because you can have virtually any length of belt and virtually any size of pulley. But one of the things that you have to be careful of, some mistakes that we've made in the past with belt drive, is that you should design your pulley length, distance that your two pulleys are apart. You should design that for the belt sizes that you have available. A couple of years ago, actually it would have been like 3 years ago, we designed our drivetrain entirely custom, and we designed our drivetrain just based off of a size or just a pulley distance that we thought, we were like, oh, it's fine, it'll work. We can just tension our pull or our belt to the point where we can drive it well. Nothing bad will happen. What ended up happening was the belt that we got was way too big, and it was impossible to tension, even though we had a decent tensioning system. And so it was either way too loose, way too tight, and our tensioning system would slip over time, and it was just not. And we'd have skipping all over the place, where our pulleys would turn and they wouldn't latch onto our belt, and only our motor would be turning, but our driven component would not be turning at all. And we learned from that point. We ended up just right before our first competition scrapping the entire belt system and replacing it with chain, and that worked way better. But the moral of the story there is that belt works really well and is a great way of transferring power if you are precise on your belt size. So you calculate the distance based off the belt size that you have available, instead of just winging it and relying on your tensioning system to take up all of that extra slack, or even having a belt that's too small, which won't be able to fit over your pulleys at all. But if you do adhere to that spacing and have that to be exact, there is very little backlash. Unless you're doing something incredibly wrong, your belt is a lot less likely to break than things like plastic chain, and it is not very prone to slippage again if you get that tensioning very down well and your spacing is exact.
All right, so this is our last thing, a gear drive. Some pros of this is that there is a semi-flexible motor position, like you can have the motor on pretty much any gear that you want, and there is a variable gear ratio. Just try not to go too extreme, because that can put a lot of stress on the motors. Some cons of that is that they can slip and grind, so everything loosens over time, and if it goes too far, then the gears can slip and grind. And there are also multiple points of failure. Even gear teeth, if as much as one gear tooth breaks, that can cause extreme problems within your drivetrain, and you might have to take apart it just to replace one gear.
And then some tips and tricks we learned over the years is make sure you know when to use the different types of shafts. So D shafts are usually pretty good all around, but hex shafts are really good for strength when you really need those shafts to lift something heavy for such. And making sure that your structure is strong and reliable. So you want to use your C channels as metal, usually for structure, instead of like brittle plastic that could easily snap. So you make sure you can have your robot as strong as possible. And then you want to prototype in CAD to make sure that all of the mechanisms are completely thought throughout and to the best ability before, and will work to the best ability before you can put everything together in the CAD to see to try to leave all the problems out before you try to put everything together. And make sure that you can fit all of the different mechanisms onto your drivetrain. This may sound a little stupid, but if you don't choose the right drivetrain, such as a bigger one, you may not have enough room to actually fit your intake, for instance, onto your drivetrain, which would leave you with problems and probably having to redo your drivetrain. And here's another question break we have.
We'll just wait for a little bit and just to see if anybody has any questions. If you do, now it's time to ask them. We'll give you a minute or so, and then if everything's good, if everybody understands, feel free to move on.
So when you consider drivetrain, you're also considering the base frame, right? The 4 structural components that will, so those need to be planned as well. Or is it always like a square or based on the dimensions in the game manual?
Yeah, so every year there is an 18-inch size limit, so your robot will have to fit within that. And yeah.
But additionally, the drivetrain methods that we've mentioned are very specific to your wheel configuration. You have some flexibility beyond that with what shape you want to put those wheels in. It does matter for some of the drivetrains that I mentioned earlier, like the X drive and the box drive. But the shape of your robot, in order to accommodate those wheel positions, is only for those wheel positions. Anything that does not go into where those wheels are being placed is completely flexible and up to you. That being said, for our use cases, we do design our structure along with our the method of drivetrain that we use. Typically, it's a mecanum drivetrain because that's what we found to be effective for 90% of the challenges of the game challenges that you would have to face. But if there was a reason that there was a game reveal and we saw something that we were like, oh, mecanum drive just won't work, we're going to have to use 6-wheel, which is something that we did 4 years ago. Then we still designed our structure and our main frame for our drivetrain at the same time as we selected and designed our drivetrain method and what sort of drivetrain we used. Does that answer your question?
Yeah, and yeah, they go hand in hand basically.
Yes, that's
your wheels and structure will probably determine.
Yes, most likely.
Yeah, because you had mentioned that the intake, you could probably have the front channel open if you have to take an intake from there and pull it up.
Yes.
So there's flexibility available.
Yes.
Yeah. Thanks.
All right. Do we have any more questions? We've had very good questions so far, I've got to say. All right, I think we're good to move on. All right, so now the bread and butter of your robot. This is what is going to vary a lot from mostly from year to year. This is what depends most upon your game challenge. So at our brainstorming session, this is what we spend the bulk of our time on, because typically your drivetrain is something that is not too dependent upon the game challenge, unless there's terrain elements, which there is likely to be. But even then, the bulk of your time is figuring out your mechanisms, what works for the game task that you need to figure out, and what suits the things that you need to do the best. And in order to make good mechanisms, you need to have a consideration for what parts to use. And I think at one of our past workshops, there was some questions about what parts are good to use. Pardon me for a second. And these are some links to the some of the most common vendors and their kits. And I'm going to put these links in the chat at this moment. These are FTC kits that they recommend for people to use. So these will contain lists of all of the different pieces that they recommend an FTC competing team would need. Now, there are some more in-depth and maybe some more obscure parts that they would offer, but typically what I would recommend is that you pick one of these vendors, either Gobilda, AndyMark, Rev. Pitsco is the company that makes the Tetrix building kit parts, or Vex Robotics. All of these parts, save for maybe the parts in the Vex Robotics kit, will be FTC legal. And the reason I say maybe not so much for the Vex Robotics kit is because they also have some control parts there that are used for the Vex competition, which would not apply to FTC. So I recommend pick one of these vendors, look through their parts. You don't have to buy the starter kit because a lot of times they can be expensive. But again, I know there were some people at one of our last workshops that were wondering about what are some of the commonly used parts. These kits will contain a list of the commonly used parts, and these are the things that you're going to want to look at buying and purchasing for you to use for your kit parts for creating your robot.
And the game process is basically the process of way you find a way to pick up and score your element. The first thing you want to do is make your intake to pick up the game element, which is pretty obvious. And then you want to find the intake that best suits the way you will pick up the game, the shape, usually the shape of the game element, which we'll cover later. And then you want to take teams the game element and take it from your intake to your output, and from the intake level into the output level. And then finally, you would want to drop off the element into the scoring container. Obtaining elements. So next you'll learn a few things about what you should consider before choosing your intake. So the first thing you have to consider is the intake type. There are a few different main types of elements. First, usually chooses to choose as the elements. And usually that's spheres, cubes, and there's also the chance that it might be an unorthodox size. So spheres can be in various sizes as long as cubes too. These can be in various sizes, so they don't just have to be the normal the cube that we saw last year season in the Wolf of Wall. We also saw they could be a lot bigger or even maybe possibly smaller than that. And unorthodox elements might be the rings you see at the bottom, but there were also some kind of relic things before. They kind of look like humans a little bit. And those, all you had to choose which element or which type of intake would be the best way to intake that.
So there are some things that you have to think about before you choose which collection, which collection mechanism is best for you. And those are how reliable it is, how much lineup it takes, which means if you can either come at it from any angle and it'll still work effectively, or if you have to spend more time lining up and getting into the right orientation and speed to pick it up. That's what the minimal lineup. How fast it is, how long it takes to get from the field into your robot, how versatile it is. If you have games that have different elements, like we've seen a lot with, you have both spheres and cubes, or maybe something even more varied than that. If you're in, how versatile it is in being able to pick up as many of those different shapes with the same mechanism, and as well the shape of the game element, because certain different types of intakes will work better with cubes or larger cubes for smaller cubes, or spheres, or different other types.
All right, so this is the gripper. As you can see, it looks kind of like a claw. And a pro of it is that it is extremely versatile for an element shape. It can grip many different things, spherical items, cubical items, like Justin mentioned earlier, unorthodox items. It can pick up pretty much anything. But some cons of it is that it has an extremely limited range of motion. It can't go backwards, or it can't pinch too far in. And it requires extremely precise lineup, because these objects can move and roll around in the field a lot. And it's also an extremely time-consuming collection process, because normally you can only pick up one element at a time with the claw.
And then there's overhead spinning. This is one of the fastest ways to collect the items. It's good for small. Usually, it's good for smaller objects instead of larger ones. There's very little lineup for this. It is hard to find the best material for this because you can in these pictures you can see many different types of materials we have. We have rubber bands in that top picture, and it looks like we have like one of those pool noodles in the bottom left. And we have surgical tubing in that right picture. So you have to do some material testing to see which one best suits the material or the objects you have to intake this year in the season. And they can often be used to it takes up lots of space to for these intakes, because you can see in these pictures that especially that top one, all that rubber band stuff is the part of the intake and transfer, which would be hard to especially if there's a different scrolling element, it would be hard to keep the size obtained.
Next is dual side spinning, which is similar to overhead spinning in that it's active the entire time and it's always running and taking in many different objects. What we found is that this is most useful for larger objects, and especially flat-faced objects also it works well for. But especially for objects that you don't need to take in like exceptionally fast. So they were pretty common in the Skystone game where there was a lot of surface area on the sides and you could only hold one at a time. I've also seen some use for these in the I believe there was some FRC games where they had a larger space to work with. They also had a larger element to take in that and they could just spin on the sides and have that element sit basically inside of their robot, where they didn't need to take in a whole bunch of really fast things all at once, but they had a larger element that with a lot of surface area on the sides that they could grip onto. Similar to the overhead spinning, I'd say even more so. There is very little lineup that's required because your side spinning elements are going to be directing everything around you inwards towards your robot. But one of the cons is that it's great for larger things with surface area on the side, but it's not as great for things like smaller balls or even like really small cubes.
All right, so this is the passive intake, and as you can see, there's a few different types of things that this could be. It could be a scoop, a fork, a cup, etc. This is an extremely easy intake to build. You literally just build whatever you're gonna build, like a scoop or a cup or something, and then just attach it to your robot. You don't need motors or servos to operate it, but it is also it can be really hard to line up because it depends on what element you have in the game, but it can be extremely hard to line up, and it's not very versatile. Like you couldn't basically have more than one of the like different type of element in it because it can be really hard because it's not versatile.
All right, this is our second to last question break. So if you have any questions about anything that we have asked or anything that we've talked about so far, feel free to ask it now, or just anything in general that you're about building or that you have any questions about, feel free to ask. So I see one question that says, when you design the robot, do you also consider the center of gravity? Do your CAD tools provide that information? The answer is yes, we do consider the center of gravity. We're actually about to talk about that a little bit but we're not going to go into depth, so I'll provide some information about that. But we are about to talk about lifting and some of the gravity considerations that you need to consider for that. But this past year, actually, we ran into some issues because we had a lot of mass that was out on the end of these giant rotating slides. And when they were extended versus where they were in, that would change our center of rotation on our robot. because of where our center of mass was. We do our CAD tool, SolidWorks does have simulations and analysis features that can be run to figure out the center of mass. We have not looked much into those, although they are very, from what I've heard, they're very effective tools. And if you were to get a sponsorship from SolidWorks and you are concerned about center of mass and center of gravity, that would be a great tool to look at, and a great way to calculate where your center of mass is. But the point is that with your center of gravity, you just want to make sure that there is no situation where your robot will be tipping itself. And you also want to consider the mass of everything on the end of the things that you're moving around. Because if you add too much mass on a moving mechanism, then when that mechanism moves, the center of mass in your robot is going to move, and that could either lead to tipping, or it could lead to changing your center of rotation, or it could lead to just some unwanted inertia that you don't account for in the rest of your design. And then we have another question that says, according to RM02 page 31 in manual part 1, the Vex claw assembly is an illegal part. This is true. I believe there must have been a misunderstanding in that we are not recommending that you buy the Vex claw kit parts and just assemble that kit and slap it onto your robot. I apologize for the confusion. We were simply using that Vex claw as an example for what one of the claws potentially is. You can use a similar design to that geared closing mechanism. We don't want you. It's obviously not legal to buy that kit part and put it onto your robot, because then you're not designing that part and that mechanism. So again, we're sorry for the confusion that we may have caused, but that Vex claw was an example of just something that can be used, that has a versatile shape that can grab several different elements, and could be an example of something similar to a design that you may want to put onto your robot or consider in your brainstorming and mechanism design. Okay, do we have any other questions? And if there's any questions that we've answered that you want us to explain something more in depth, or something that we didn't go through thoroughly, or something that we explained that you don't understand, feel free to say something in the chat again, and we'll do our best to keep on going at that. I'll wait for another minute and then we can move on. All right, I think we are good to go. All right, so transferring elements. This is where the weight of whatever you are creating does really come into play. These are some of there are more ways to transfer elements. These are simply some of the ones that we have a lot of experience with. And we're going to go into depth with the single bar, chain bar, 4-bar, and linear slides. And the purpose of a transfer really is to take your game element from the field where it is starting, or actually more accurately from your intake, wherever it lands after your intake, and to transform it into a more scoreable position that you can then benefit off of and get points from. So the unspoken truth is that first loves lifting things. There will almost always be an elevation change in the game, and there will almost also always be a smaller goal and a higher goal, and a goal that is just for pushing things around. And that is First's way of challenging you and still allowing teams that cannot potentially lift things as high, still allowing them to get an amount of points and still compete and put time into a somewhat competitive robot. Most of the games that you will have will benefit from a lifting mechanism. However, we have seen in the past with games like Velocity Vortex and Ultimate Goal that can occasionally look like lifting things with a shooting mechanism, where you are launching things out of your robot and into a goal. So that just depends on the game. So some things you have to consider: stability. Stability has to do a lot with how wide your lifting mechanism is, but again, also that weight component, how much weight you're putting on the end, the height, how far you need it to go, and how far, how again, also how that affects stability, because the higher and the further you get it away from the base of your robot where a lot of your weight is, the more likely you are to tip. How fast you can get your mechanism and whatever you have up to that height, because the name of the game at the end of the day is cycle time and how quickly you can get your game element from one place to another. So the quicker you can do that, the more points you can get, the more effective the more effectively that you can earn points. The weight of the end effector, again, this big thing where you don't want your robot to tip, that could put you out of commission for the entire robot. So you want to, in an ideal world, keep that weight as low as possible. But if you do add that weight, just be wary of the inertia that's going to add. It could potentially slow things down. It's going to put a lot of force on your robot when that extends out, when especially the acceleration that it will experience when it stops. And that's just a lot to think about. So just make sure you're aware of that. And if you are adding a lot of weight onto the end of a lift or a transfer. And also all of the ideas that we're going to talk about for lifts could be, these are just basic concepts which can be adapted, changed, combined, you name it. These are just the bare bones examples. And finally, you have to think about what space you have. Some of these lifts take up more space than others. And as we talked about with the drivetrain, it's very important to be able to fit all of your mechanisms into one area and to design so that you know that you can fit in that 18 by 18 by 18 cube at the end of your design process.
All right, so this is the single bar lift, and it's the easiest and most simple lift you'll probably see in your FTC career. So some pros of it is that as I said, it's extremely simple. There is only like one sort of joint, as you can see. And some cons of it is that the element can change orientation, and it has an extremely limited range of motion. It can't go back. It can't go like backwards, and you can't drive it forwards too much, or else it will put a lot of stress on the claw and the lift, and it will break eventually.
The chain bar is a relatively simple and easy to make system, but is usually stays in the same way. The object you pick up usually stays in the same orientation that you pick it up the way it is, because is moving parallel to the origin of the where the motor's at. It's not the best reach. You might have to get an extender to this chain bar. So like last year we used a chain bar to cap our team shipping element, and we had to put our chain bar on our slides to get a higher extent with this chain bar. So chain bars are not always the best way, are the best way to get from low place to a very high place in the field. Then 4-bar lifts can be as complex as you want them to be, with the easiest one of the easiest ones being on the picture on screen. And one of the most complex is the double reverse 4-bar, but it could just be a simple 4-bar lift like the one on there. And then these so that the 4-bar lift, which is displayed on the screen, is pretty similar to the chain bar lift, but it has instead of the chain keeping the output parallel, we have two pieces of, usually it's metal, keeping the side parallel. And the double reverse 4-bar is not a picture you can see here, but it basically the end of it is in the same place where the base of the structure is. So this would be a little bit better for space reasons. And then there's also the 6-bar lift, which can be is definitely more complex than the 4-bar lift, but it's relatively the same with 6 bars instead. And
Okay, so before we get into the next lift type, I'm realizing, or I was notified that we missed a question, so I'd like to apologize for that. Somebody asked, "Is there a recommended belt width for traction, i.e., 1/4 inch?" And so I'm going to answer this. I'm not entirely sure. There's some clarifications that I'm not entirely sure about, so I'll answer this in a few different ways, and then if that doesn't answer it exactly for what you're asking, then feel free to add something else in the chat to try and clear that up a little bit. But so I'm not entirely sure on whether this is asking for a belt width that allows for better power transmission for traction on wheels. Like say you're driving from a motor to a wheel, what width would give you the best traction for that wheel? Or if this is asking if there is a recommended width for using that as more of a conveyor belt, which we've seen for transfers before. And the answer for the first one, where if there is a recommended width for driving from a motor to a wheel, if there's a best width that would give that wheel more traction, the answer is that as long as your belt is wide enough to not slip and wide enough to give your all that power transmitted from your motor to the wheel without any problems and it's properly tensioned, then the belt width doesn't really matter for that. But it does help to use what are called timing belts and timing pulleys, which have teeth in them, and that will help with your traction and reduce slippage. So if your question is about from the motor to the wheel, my answer would be the width really doesn't matter, but there are different profiles for timing belts. Like we use HTD belts, which is the name of the profile, which is the shape of the teeth of the belt and the teeth of the pulley. And then if the question is about using the belt as a conveyor and having something ride on that belt, having traction for that, which is again something that we've seen before and thought about in prototyping, I would say that honestly would take to find the best amount of traction, that would take probably the best thing that you can do is some testing for that, and try and do some trials and maybe some coefficient of friction calculations. We personally have tried several different times to use that sort of transfer method, and in the end, in our parallel prototyping process, other transfers just ended up winning out. So we haven't really developed that to a large extent. However, something that we have tried for that sort of a concept is something called flighted belts, which are used a lot in manufacturing in order to move packages from one place to another, where there are little bumps or ridges that are spaced out at an even spacing where the thing that you're moving can fall into those grooves and then get from your starting place to your ending place. So again, I'm not entirely sure which one of those two that I was asking, but if that answered your question, great. If it didn't, and there's something you want me to go into more detail with, feel free to put that in the chat. And then for our next question break, I will revisit that and any other questions. So getting back to our transfers and our slides, our final type of transfer and lift that we are going to talk about is our linear slides, which is the one that we tend to use the most, I would say, our team personally, and that we've seen a lot of success with. And these are very common in FTC, and there's a lot of different ways that you can do them. So they're very versatile. We personally use Mizumi drawer slides. They do have some wobble and some shake in them, which can lead to some inconsistency, but they're better than some of the other drawer slides that we've seen, and they offer some good mounting options. So any sort of drawer slide would work. The idea basically, it's like, you know, a drawer slide slides in and out. You are sliding your whatever you're moving, just instead of in and out of a drawer, it's going from in your robot to up above your robot. And these are typically driven with either string or chain, or sorry, string or a belt. and there are some diagrams here of how that works. We typically use a cascaded stringing method, and you can see this in the depiction of the robot holding the ball on the right. That is what is known as cascading, where you go from your driving pulley through to your first stage, and then instead of going from there to your second stage, you have your second stage has its own set of stringing that ties back to the bottom of itself and the top of your first stage. This way, when you extend your first stage, all of the rest of your slides will extend at the same time. This makes it very fast, very efficient, and this is what we found best to work with. But what you can also do is on the same picture on the left side, as you can see where you run the string through all of your different slides, you have a pulley at the top and bottom of every stage. And this is slower because it will go your first stage, then your second stage, and your third stage, but it is still effective. And then belting is very similar to that same idea. Or you can use either method, but and you can do it in either way. And belting is honestly less likely to break than strings. We've had some issues with strings breaking in the past. However, the way that we've combated that issue is we've done some material testing for strings, and we found especially that plastic reinforced strings that you can buy on Amazon or Kevlar reinforced strings are less likely to break. But if you want to avoid the issue entirely, going with belts is is definitely an option. And again, think about your end effector. This method is very susceptible to it, especially because you have a lot of movement, especially if you're going from having these slides going horizontally as opposed to up and down. There is a very good chance for tipping because you are moving a lot of weight very quickly around your robot in a very precarious fashion.
Next, we'll be going over scoring elements, types, and tricks to how to get points. So there are a few different types of ways first makes us score. So there's the 5 main ways is launching a material into a goal or something like that. Maybe dropping one of the scoring elements into a container to score points, pushing something into usually the scoring element into the goal or something, and balancing either that could be your robot or the again the scoring elements, and lifting stuff in place to score points.
Some tips and tricks for scoring elements. So as I mentioned earlier, the name of the game here is cycle time. I mentioned that, I believe, back for one of the intakes, I think. But the important thing is that you want to be able to take whatever game element you're working with from its position on the field to the scoring location in a very repeatable, quick, and simple way. The reason you want to make it simple is because simple things are a lot less likely to fail, and then you can have a lot better of a prediction of how your robot is going to perform. And that is very appealing to robots that are looking for an alliance partner potentially. Because if a team knows what your robot will be able to put up and they've seen it consistently put up that score using a simple design that works quickly and reliably, then they know that they can add their capabilities onto yours. And additionally, keeping something simple and keeping something reliable is just a good engineering practice. From my experience, from when I've been to competitions and seen teams perform and robots perform, the teams that can consistently put up a mediocre score are going to place higher and do better than the teams that can put up a really high score maybe once, but then something breaks or something isn't working, and they put up lower scores for the rest of the day. That's something else to consider for scoring elements is the driver ease. This goes also into programming, which we're not going to dive deep into in this workshop, but if the drivers are putting in less effort and it's on the robot and it's on the engineering, then again, that's also going to lead to more consistency. And something else for just basically all of the mechanisms is doing your research on past games, other teams, and industrial examples like we mentioned earlier, because at the end of the day, first is about cooperation, helping each other out. Everybody's trying to compete to their best. Obviously, don't just steal somebody else's design with no like thought or input of your own. But a lot of the times, the best designs come from your own input as well as inspiration from others, where you're able to see something that somebody does and go, oh, that's a neat idea. And then you take your experience and you add on to it and create something that's entirely new and are really unique, but based off similar principles, perhaps, and that functions in a way that works best for your team. And that brings us to our final question break. So I am not seeing any follow-ups from that question for earlier, so I'm going to assume that that is good for that. But again, if you have any final questions, please feel free to put them in the chat now, and we will get to them. Anything about the presentation overall or any build questions, we'll be more than happy to answer them. And this is your last chance for this presentation. So feel free to put those in to the chat. I do see a question that says, is there a recommended drive speed for shaft driving a mechanism wheel? And the answer to that is, it depends greatly. It varies greatly off of depending on your different design specifications and from team to team. We personally use 435 RPM motors, I believe, for our 4 drive motors, and then we gear them for speed. And that's personally just what we've found to work. But that also is because of we found that based off of the weight that we tend to make our robots, as well as the diameter of our wheels. That's just what we found personally works best for us. If you have larger or smaller wheels, that might not work for you because of because your robot will either go faster or slower. And if you have something that's especially heavy and then you gear it for speed, your robot for speed, then you may not be able to move your heavy robot around. So that takes a lot of testing and trial and error as well. What I'm mentioning there is the gearing that we have, the 435 RPM with the gearing that we have. The speed will vary based off of your robot input and your programming, how much power you give to the wheels. So the good thing about it, though, is that you typically, if you're driving it with a chain or with a pulley, that is something that's fairly easy to test by just buying a bunch of different pulleys and swapping them out for and seeing what works well for you and making note, hey, this feels a little bit too slow, hey, this is perfect, or this is running a little bit too fast and we need some more torque. And then you can quickly swap those in for each other and figure out what gear ratio works best for you. And then as far as just the speed goes, that's up to how you would like to program that for things like autonomous and stuff like that. There is another question or another question saying, can we have access to this presentation and access to the video recording? So this video recording will be posted on our YouTube channel. So this will be something that you guys can go back and look at if you found it was helpful. And we will also be sending this presentation out. So you will be able to look through this and go back at it without us droning on over it. And you'll be able to look through it at your own pace and make of it whatever you need to. Another question, when will last week's workshop's recording be sent? That is a very good question. let's see. It's probably tomorrow is an answer from one of our mentors, or tonight. So that will be up soon. And again, these will also be up on our YouTube channel where you'll be able to view them. I see a follow-up. Is there a recommendation? Is there a recommended belt width for traction, i.e. 1/4 inch? So again, I'm going to need some clarification on what you're asking here. Are you asking for?
No, like when you have drive trains, and you're trying to do a drive one, you mentioned, belts are not ideal. So is there a way that, if the belt width, you have a 1/4 inch or a 1/2 inch or something like that, then it's better to have a thicker belt over a smaller belt for belt drives?
In order to prevent slipping from the motor
Yes.
to the wheel?
Mhm.
Okay, so give me just a second. I'm going to pull up something here real quick. So in my experience, at least, the width of the belt does not typically have as much of an impact. Although I am going to Justin or Jake, can you stop your screen share for a second? Okay, so I don't know if you can see this, but so the types of belt, we didn't really talk about this very much in the presentation, but the types of belts that we use, there are round belts, which are just like rubber bands. Really, they have nothing to them other than just the size of the belts, or I guess they're probably more like hair ties, although not elastic. So round belts are not are good because they will slip if you get too much torque, because there's nothing really holding them in place. They're just there. But what we use for our drivetrains is these, what you can see up here on the screen, these profiles for timing belts. And this is what I would say is more important when you're looking at traction from a belt on its pulley from your motor to your wheel, as opposed to the width. Typically, any timing belt that you buy from a robot parts seller like Builda, or from any of the kit vendors that we put out into the chat, any of those timing belts that have a decent profile will have a width that is more than enough to supply enough traction. We use, on our team, we use HTD belts because that's just what we found to work. The pitch of the belt, which is this measurement here, is what is going to be actually, no, I don't think that's the pitch. Sorry, I misspoke there. But the point is that if this were your amplitude, if this were to be, I guess it is what it'd be considered, but your depth of your teeth is going to be what is most important for that traction. Yeah, I don't know if that answers your question, but this is I would say this is the most, when considering what belt to buy, this is the most important factor for traction, and HTD is what we've used, and we've had very little issues with it.
Okay, yeah, this is good. So that's like a corrugated belt that will have.
Yeah, it's like a corrugation.
Yeah, thanks.
No problem. All right, and then Jake, if you could put up the, yeah. All right, do we have any more questions? Anything at all? All right, I think we're good.
Yeah,
so this is the so I'm sorry, was there a question?
No, not a question.
Okay, cool. So I think we're good to move on. So this is our Twitter and our email. Thank you so much for coming. This is the final of our 3 workshops in the series. So hopefully you enjoyed it or learned something. Our goal is to give you a jump start if you're a rookie team or maybe have been around for a year or so. Just some of the learnings that we've gone in our past 7 years. Hopefully, we can pass that on to some teams that maybe will give them more of a better starting position at the start of their season. Feel free to reach out to us through our email or our Twitter. Literally anything we're happy to help with. We programming, business, build, whatever you want. And again, these presentations will be recorded and the presentations will be sent out and the recordings will be put onto our YouTube channel very soon. So thank you again for coming. If you have any questions again, feel free to put them in the chat. But if that is all, then thank you and have a good day.